This circuit is not a series or a parallel circuit, it's both. If we trace the possible currents, we could leave the battery, go through this resistor, get back to the battery. But there's three other paths that share something in common. Several resistors in the battery, but also have separate places. The way to do this is to recognize that part of the circuit is in series and part is in parallel. These three resistors are in parallel with each other. They each have their own current, and they're each connected to the exact same place in the circuit, this junction here. These two resistors are in series with the whole rest of the circuit. So what I was taught, and what I'd like you guys to do, is to visualize the circuit in progressively simpler pieces. The first thing we're going to do is we're going to combine the three resistors that have the most in common, and that is these parallel ones here. We're going to say that all of these guys are part of a new resistor, RP. And RP will be a single resistor that we can yank these guys out, plug RP in there, and there'd be no effect on the rest of the circuit. So we'll make the circuit progressively simpler. So we'd still have a 9-volt battery. We'd still have a 100 ohm resistor. We'd still have a 37 ohm resistor. But we'd have this new resistor here, RP, that actually replaces the 81, the 92, and the 156. And then after we complete this step, these three guys have a very simple relationship now too. They're in series with one another. So we can combine them using the other rules we've learned for combining series resistors. So we still have a 9-volt battery, but that's all we would have. We would then have combined all of the resistors into a much simpler circuit with one resistance. Now, what's the point of this? If we get down to this super simple circuit, we then can figure out the current in that circuit. Well, that will be this current here, and it would have been this current here as well. And it's also the current through two of our resistors. With that current, we can use Ohm's law, and we can figure out how much voltage each of these guys get. That in turn will give us the voltage everybody else gets, which lets us use Ohm's law again to figure out how much current each of these guys get. It's a complicated process, but it always works the same way. So if you practice a few of these, and we'll do some in class, but you'll always have this video to watch, you'll learn the process. It's basically take the whole circuit, make it progressively simpler until it gets as simple as possible, and then build your way back out and find all the relevant voltages and currents. So the first step in simplifying our circuit was to take the parallel ones and put them together. So let's do that. As we saw from the parallel video, 1 over RP is going to be 1 over R1 plus 1 over R2 plus 1 over R3. And that R1, R2, and R3 are these resistors. This looks somewhat complicated, but this equation is more bark than bite as long as you use a calculator and you pay attention to the order of operations. So the way I'm going to enter that in the calculator is I'm basically going to write parentheses 1 over 81 parentheses plus parentheses 1 over 92 parentheses plus parentheses 1 over 156 parentheses equals. So we get 1 over RP is 0.0296. But I'm not even going to Plug that back into the calculator. I'm just going to hit the inverse key. And that gives us a RP of 33.75 ohms. So it's as if these three guys, their place could be taken by a single resistor of 33.75 ohms. Now, notice that's smaller, which is exactly what we expect, because these resistors, adding each of them in opens a new road, a new path for electrons to flow. So we expect having three of them there, three roads, would decrease resistance. So if you built this circuit, which we won't, you won't be able to find a resistor like that. The 100 and the 37 wouldn't even notice. And that's the whole goal here. By making these progressively simpler ones, we can find out information for circuits we can't actually build. So now we're going to combine all three of them together because they all three share a current, and that makes them a series circuit. So we're going to combine them all in series now and see what that would be. Now resistors in series are very simple to combine. RS would be R1 plus R2 plus R3. And in that case, RS would be 100 plus our new RP plus 37. What did this get us? It got us the ability to find a current. The current through this battery, which is the same as the current through this battery, which is the same as the current through this battery. And this picture shows that it is actually the entire current for the whole circuit and for anything that the whole circuit's current has to pass through, including the 37 and the 100 ohm resistor. So this useful piece of information, this total resistance, we can use Ohm's law to figure out what the current through the battery is. So let's do that. We have V equals IR. We have a voltage of 9 volts. We have an unknown current. And we have a resistance of 170.75 ohms. What's nice about that is that's not just this current. It's not just this current. It's this current. So now we can backtrack and we can start finding out all the other information. So the next step is to recognize that this current here also goes through the 100 and the 37 ohm resistor. They have identical currents. So we can now do Ohm's law for these two parts. This is going to be V equals IR. Its voltage is going to be 0.0527 amps times its resistance, 37 ohms. 1.95 volts. This guy up here, his voltage is going to be the same, 0.0527 times 100 ohms, 5.27. Guess we could have guessed that. 5.27 volts. So, what did that accomplish? Since these guys are in series with one another, and this is 5.27 volts, and this is 1.95 volts. The parallel resistors, they get what's left over, according to Kirchhoff's loop rule. You go up 9 volts, you go down 5.27, you go down 1.95. You have to go down farther, and the rest of it is whatever you drop in this section of the circuit. All three of these guys will have the same voltage because they're parallel to each other. And now we can use Kirchhoff's loop rule to figure out what that is. 9 volts is equal to 5.27 volts minus RP plus RP. These are equal to each other. Plus 1.95 volts. RP is 1.78 volts. Sorry, I did not write this correctly. This should be the voltage across RP, not RP. So I want to re-emphasize that since I messed up. You go up 9, you go down 5.27 volts, you go down 1.78 volts, you go down 1.95 volts, and now you're back to 0. So in this resistor RP, we've got this much voltage. Since these guys are all in parallel, it will all be the same. And now we can finish up the doing of this circuit by using Ohm's law for each part left over. V equals IR will be true in each of these 3 branches. So we'll very quickly do that. So in the 81 ohm case, we have V equals IR. Well, the voltage is 1.78. We don't know the current, but the resistance is 81. So we can go ahead and copy these now to these amp meters. This is 0.022, 0.0193, 0.0114. I hope those numbers aren't surprising. The majority of current flew through the branch with the smallest resistance. And now we're pretty much done with all the tough calculations here. We should use Kirchhoff's junction rule to check that they're true. If Kirchhoff's junction rule is correct, which it is, these 3 currents flow into this junction. So this current, the total current, should be equal to the sum of the 3 of them. So just checking the currents, 0.114 plus 0.0193 plus 0.022, 0.527, which is our total equation. We've learned how to calculate the power, the energy per second that electronic components dissipate. That is calculated using the equation power equals current times electric potential or voltage. And I just wanted to point out that for a complex multi-branch circuit, the first steps for finding the power that each of the resistors dissipates are exactly what they were before you knew about power. You find the voltage and current. And now when you have all that information, you can go back and calculate the power, the energy per second that each resistor dissipates. But if you want the power for each resistor, all you do is multiply the current and voltage. So let's go ahead and do that. The power for 100 ohms would be, its voltage was 5.27 volts, and its current was 0.0527 amps. You're just going to go through and multiply all the voltages and currents together.